Hey guys, my name is Shreyas and welcome to Simple Chemistry. Now in the previous video we talked about how orbitals were regions in space where an electron can be found. In this video we're going to be talking about how atoms configure their electrons in within these orbitals. So the general hierarchy for the quantum mechanical model, by the way, is the current view on what's the correct model for the atom. It might change with time, we never know. But basically how it works is that we have energy levels, just like in Bohr's atom, just like energy level 1, 2, 3, 4, 5, same thing. Within those energy levels, we have sublevels. Sublevels are all the orbitals that have one shape. So we'd say, you can call a sublevel, an example of a sublevel would be 3p, which means that it's in energy level 3 and it's the p sublevel, okay? We can also have s sublevels, d sublevels, and f sublevels. Within these sublevels, we have orbitals. So an s sublevel only has one s orbital, a p sublevel has 3 p orbitals, a d sublevel has 5 d orbitals, and an f sublevel has 7 f orbitals. We talked about how the orientations of the orbitals in the previous video. So you can see here like how a p sublevel has 3 p orbitals. Each orbital represents one of the orientations, p's of x, p's of y, p's of z. If you don't know what I'm talking about, go check out the previous video. And then within these orbitals, there can be at most 2 electrons in these. They can be 0, 1, or 2, and each of these electrons will have opposite spins. Now, electron configurations, there's 3 rules which you need to know. Okay, so these are actually not rules I just made up. These are like actual rules which are defined by scientists. Okay. By the way, electron configuration is again how atoms configure their electrons. Basically, how atoms put their electrons within these energy levels and sublevels and orbitals. Okay, so the first one is the off-bar principle, which basically states that electrons enter the lowest energy levels first. So basically, you can't first an atom can't just put its first electron within the 7th energy level and then go back to 1. It has to go 1, 2. It has to go in ascending energy. Okay. The Pauli exclusion principle says that an orbital can have at most 2 electrons, and these electrons must have opposite spins. And Hund's rule says that every orbital gets an electron before an orbital gets 2. Okay, so now let's look at a periodic table and actually see how do these electron configurations work. Okay, so I have 4 regions on this periodic table here. The yellow region is called what we call the s block. The blue region is what we call the d block. Sorry. The green region is what we call the p block, and the orange region is what we call the f block. Okay, so basically when we're talking about electron configurations, we have to start at the very top with hydrogen and start moving to the atom that we want. Okay, so let's say, let's just look, okay? So let's first start with hydrogen. So we know hydrogen has 1 atom. So basically, the way we talk about the electron configuration is we start with, we know that, by the way, I did not mention this. Each row of the periodic table mentions a energy level. So this would be energy level 1, 2, 3, 4, 5, 6, 7. Okay, so we know hydrogen has only 1 atom, 1 electron, so we'd simply just say 1s1. So what does this mean? We're in energy level 1 because we're in the first row of the periodic table. Then we're in the S block, so basically we're saying we're in the S sublevel, and within that sublevel we have 1 electron. Okay, now if we're talking about helium, we say the same thing except 1s2, because we have 2 electrons. So basically same thing. First, energy level, because we're in the first row of the periodic table, and then S sublevel, because we're in the S block, and then within that S sublevel we have 2 electrons. Okay. Now, as we move down to lithium, we have 1s2 for the first 2 electrons, and we know lithium has 3 electrons. So for the third electron, we'd say 2s1. So basically, 2 of its electrons are within the first energy level, within the S sublevel. And then the second electron, the third electron, sorry, is in the second energy level, because it's in row 2. And within the S sublevel, and it's just 1 electron. Beryllium would be same thing except 2s2. Okay, then as we move to boron, this is when we enter the p block. So we'd say everything up to 2s2 except we'll go to 3p1 because there's 5 electrons, okay? I mean, sorry, 2p1. 2p1, okay? And then as you keep going, this carbon would be 2p2, same thing except 2p2, nitrogen would be same thing except 2p3, 2p4, 2p5, and 2p6 all the way to neon, okay? So let me write that neon. It would be 2p6. Now as we move to sodium, sodium would be same thing except 3s1. And then magnesium would be same thing except 3s2. And then here aluminum, silicon, so as we keep moving here, aluminum would be the same thing except now we have the 3p1, and then 3p2 for silicon, phosphorus 3p3, sulfur 3p4, chlorine 3p5, and argon 3p6. Okay, so let's move all the way to argon 3p6. And then as we move down to potassium, we just have the same thing except 4s1, calcium would be 4s2. Now, as we move to the D block, something interesting happens. So, when we move to the D block, we actually don't say that, let's say for scandium, we would not say that the 21st electron would be in 4D1. Actually, we move down, that D block is one energy level down, so we'd say 3D1, okay? It's actually not 4D1. Just remember that. Don't ever forget that, okay? And then as we keep going, the same thing. So 3D1, titanium would be same thing except 3D2. Vanadium would be same thing except 3D3. And keep going on and on. As you enter back into the P block, nothing changes. So we'd be back to 4P1 for gallium, and on and on and on. And then same thing for rubidium. Rubidium would be same all the way up to 4P6 of krypton. And then the rubidium would be 5s1. And then again, when we get into the D block, we'd have to go down one, and then we'd count the electrons there. Now, interesting thing that happens is, let's say, is another thing when we enter the F block. So let's say we're talking about one of the electron configurations for one of these elements. I actually don't even know the names of these elements because we never talk about them. Okay, but let's just say for a CE, I'm not sure what that is. So we'd go all the way up. So we exactly did 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, one level, energy level down for the D block. So 3d10 back to 4p6, 5s2, 4d10. 5p6, 6s2, 5d10, 6p6, 6p6. Sorry. We enter here. So let's just start here. So 5s2, 4d10, and then we move to xenon, which would be, yes, we move to xenon, which would be 5p6. And then 6s2, okay, so we're at 6s2, and then we're finally at barium. Okay, so everything up to barium and to 6s2, right? And then we move here. So what happens is, just like how the D subblock has moves down in one energy level, the F subblock moves down 2. So we'd say all the way everything up to 6s2, and then we move to here, we'd say 4f1. Okay, 2 energy levels down, 4f1. And then this element right here would be 4f2, 4f3, 4f4, and it goes all the way to 14. Okay, and then we'd move back, and we'd move back into 5d1 for this element here, and on and on and on. Okay. Now it might be a little confusing what the heck this means. I think when we do electron distributions, you'd have an understanding how these electron configurations represent how the electrons are distributed within the atom. For now, just be able to write this notation here, and then as we continue through this lesson, I think you'll get a better understanding of this. Okay, one final thing that I wanted to mention before we start doing a few of these practice problems here for electron configuration is that where are these numbers coming from? You can think about it like this. So let's say there was a question saying within the D sublevel, what is the maximum number of electrons that we can have? Let's just say for example, 3D, right? So we'd say the 3D sublevel, what's the maximum electrons we can have? It's very simple. We know that the D sublevel has 5D orbitals, okay, and then each electron, each orbital is going to have 2 electrons, so it's just literally just 5 times 2. So 5D orbitals, within each orbital there's 2 electrons, so 10. That's the most it can have, right? And so that's why when we look at the D subblock here, we have 10. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because it has to follow with the rules here, right? And same thing with the S subblock. Whenever we talk about the S shells here, the S sublevels, we know that the S sublevel has 1 S orbital, and each electron within each orbital within has 2 electrons, right? So it's just 1 times 2. And then the P orbitals, we go all the way up to 6, because that also makes sense. P sublevels have 3 P orbitals, and then 2 electrons are found within each orbital, so that's 6. And then same thing with F, 7 times 2, 14. Okay, so make sure you understand that. Now let's actually look at a few practice problems here. So this is probably one of the types of questions you'll be asked. Write the electron configuration for the following elements. So let's say nitrogen, right? So nitrogen, let's see here. Nitrogen is right here. I think I only have it highlighted. Let's see. It's right there. Okay. So we start here. So again, 1s2, first energy level, S subblock, so 1s2, then 2s2, and then 2p3. So that's all this is. 1s2, 2s2, 2p3. Okay, now let's do gallium. Let me just write it down here. I don't want to have to switch between slides. So gallium is right here on the periodic table, so let's start moving. So here we start with 1s2, then we move down to 2s2 for the second, the first, the third, and fourth electrons. Then the next 5 electrons, so the next 6 electrons, yes, are going to be in 2p6, and then 3s2, then 3p6, and then 4s2 here. And then again, now we enter the D subblock, so we have to go 1 energy level down, so it would be 3d10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we finally get to gallium, so that would be 4p1. Okay, and the final example here is gold. So gold is, let's just continue with this. I don't want to have to go back, right, because it's just a waste of time. So we were at gallium, so gold is right here. So we move all the way to 4p6. And then we move to energy level 5, so 5s2. And then the D sublevel is 1 energy level down, so when we move into here, it's going to be 4d10. And then we're all the way to indium, and then we move here, so 5p6 for the next 6 electrons. And then we're in the 6th energy level, so we'd say 6s2. And then now we move into the lanthanide series. So if you look here, remember that the F sublevel is 2 energy levels down. So from 6s2 we move to 4f, and then remember a filled F sublevel is going to have, again, 14 electrons, because there are 7 orbitals within the F sublevel, any F sublevel, and then there's 2 electrons per each orbital, so 2 times 7 is 14. You can also count it here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 4 of 14. And then we get to gold, which is going to be 1 energy level down, so we'd say 5d, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 5d9. Okay? So it's very simple, really. Just make sure that you don't mess up the order, of course, and also what the energy level is for each sublevel. Okay, it's pretty simple. Now, what you might be thinking is, oh my God, do I really have to do this for all these elements like indium and tin, like going all the way here? Actually, scientists have an easier way of doing this called the noble gas configuration. So let's look at the noble gas configuration. So let's say for nitrogen, we wanted to write the noble gas configuration instead of the electron configuration. So what we do is we look at the noble gas which comes directly before nitrogen. So that would be helium. Remember again that the noble gases are the elements which are in this family within the periodic table. Okay, so if you look at nitrogen, the noble gas that comes directly before nitrogen is helium, right? So move back up to helium. So what we do is, instead of writing the electron configuration up to helium, we just put helium like this in brackets. So what this is saying is that we're accounting for all the electrons up to helium, and then only would we put the electrons up to nitrogen. So we just put He for helium with the brackets, and then we just say 2s2, 2p3. So that way we are saving time. I mean, not really for this, but for gallium, this would make it a lot easier. So for gallium, we look at the electron, the noble gas, which is directly above gallium. So that would be all they move up argon. So we just put argon here in brackets, and then from argon we can start writing our the rest of the electrons. So that would be 4s2, then 3d10, because again the energy level is 1 down, and then 4p1. So 4s2, 3d10, 4p1. Okay, and then this is also going to save time for gold. Gold is all the way over here, so we just look at the noble gas which comes before gold, which is xenon. So we just say xenon, which is indicating the electron configuration all the way up to xenon. It's just kind of like just abbreviating it there. And then from xenon we can start writing the rest. So from xenon we're here, so this would be 6s2. We again move into the lanthanides series, so that's 4f14, 2 energy levels down, and then finally to back into the d orbital, which is d sublevel, sorry, which is 1 energy level down, so 5d9. So 6s2, 4f14, 5d9. 6s2, 4f14, 5d9. So it's basically the same thing as electron configurations, except we're using these noble gases in order to save time. Okay, I think I'm just going to stop here, and then in the next video we're going to be talking about electron distributions. Just make sure that you can write the electron configurations at this point, even though you might not have a clear understanding of exactly how the electrons are being placed within the orbitals, and in the next video you'll get a better understanding of that. For now, just be able to write these configurations, even though you don't completely understand what they are, and know these rules. Okay, off-bar principle, Pauli exclusion, and Hund's rule. We'll be getting more into depth in the next video, and then also be able to know that what energy levels are and what sublevels are, and be able to, like how I said that the F sublevel has 7 F orbitals. Make sure you just study this information and understand that know the maximum number of electrons which can be in each sublevel. And we have a very comprehensive quiz to make sure that you understand everything. And if you're able to get a 100 on that quiz, then you know for a fact that you understand this material. Okay, so that's it for now. In the next video we'll talk about electron distribution, so you can have a better understanding of how these electrons are really being distributed. But for now, electron configurations are as simple as that.